The algorithm works on a flow network, which is a directed graph with weighted edges, like the one we have here. Visualizing the edges as a series of pipes and the flow as water will make the concept much easier to understand. There are two special nodes in this graph. The first is the source node, the green node marked S on the left. This is where water enters the system. The second is the sink node, the red node marked T on the right, where the flow leaves the system. The weight of each edge represents the capacity of the pipe, which is the maximum flow that can pass through it. The question is, what is the route from the source to the sink which maximizes the value of the total flow through the pipes? Let's go through this graph and find the maximum flow. Let's start by pushing 15 units of water from the source to A. Notice that the text on A is turned red. This is due to the conservation constraint. Water can only enter the system from the source node and exit the system from the sink node, so the output from the source, which is labelled here, must equal the input to the sink, labelled here. This means that if 15 units of water enters A, 15 units of water must leave A. We now have a valid flow through the graph. However, this edge has 5 remaining capacity. This is known as the residual capacity, and it is calculated as the capacity of an edge minus the flow going through it. A residual network is formed from edges which have a residual capacity greater than 0, which at the moment is every edge on the graph. An augmenting path is a path from the source to the sink, where each edge has a residual capacity greater than 0. If an augmenting path exists in a graph, that network will not be at max flow. Let's increase the flow through the edge connecting S and A to 20, which decreases the residual capacity to 0. We must also increase the flow out of A to 20 to conserve flow. These edges are now critical, that is, the flow going through them is equal to their maximum capacity, and their residual capacity is equal to 0. This is still not the maximum flow, as we have an augmenting path connecting S, B, and T. We can push 10 units of water through the pipe connecting S and B, and 10 units from B to the sink. Although this edge still has a positive residual capacity, the flow is bottlenecked by the critical edge connecting S and B. The total flow through the graph is now 30. As there are no other augmenting paths available, this is the max flow of this flow network.
Now let's show how the algorithm works, by showing how it can be implemented in order to calculate the maximum flow. We'll be looking at a pseudocode implementation of the algorithm. For input, we need a graph defined by capacity matrix and a neighbor list, as well as a source and a sink node. The algorithm will return the maximum flow through the graph, as well as a matrix giving a legal flow of the maximum value. To begin, it initializes the flow through the graph to 0. It then enters a loop, where on each step, it tries to find the shortest augmenting path from the source to the sink using a breadth-first search. The breadth-first search returns 2 values, the capacity of the path found and the parent table. If the breadth-first search returns a capacity of 0, it means an augmenting path could not be found. If no augmenting path is found in the residual network, the network is at maximum flow, which causes the algorithm to terminate. It returns the maximum flow through the graph and a matrix containing the flow path. However, if a path is found, then the algorithm will add the capacity returned by the breadth-first search to the maximum flow variable. The algorithm will then use this augmenting path found to update its residual flow graph, which on the first iteration is simply the original input flow network with a 0 flow. In order to update the residual flow graph, it finds the edge with the smallest residual capacity in the augmenting path, which is the flow that the algorithm will be adding to the network on this iteration. Then, on each edge contained in the augmenting path, the algorithm will subtract the minimum residual capacity found from the edge capacity, and then add the residual capacity to a backwards edge going in the opposite direction between the same 2 vertices. The algorithm will then loop back to the beginning, where it attempts to find another augmenting path. Let's put the algorithm to the test on the example we solved earlier in the simulator. The graph has 4 nodes, where S is the source and T is the sink node. We start by creating an initial residual graph with the flow initialized to 0. Then we find the shortest augmenting path from the source to the sink, which in this case could be S to A to T or S to B to T, both with length 2. The algorithm could choose either of these first, and so we'll be choosing S to A to T for our example. The minimum residual capacity of S to A to T is 20. We now update the residual graph for the augmenting path, subtracting 20 from both forward edges, which are S to A and A to T, and reducing the capacity values to 0, effectively removing them from the equation. We then add 20 onto their backwards edges, which are a to s and t to a. On the next step, the algorithm will now attempt to find the next shortest path, which is s to b to t, which has a minimum capacity of 10, due to the edge s to b only having a maximum capacity of 10. We now update the residual graph of our new augmenting path, subtracting 10 from s to b and b to t, and adding 10 to b to s and t to b. At the third step, there are no remaining outward edges from the source, and so we cannot find any additional augmenting paths. The algorithm will now terminate, having found a max flow of 30.
Max flow problems are prevalent everywhere in the real world, found in electrical circuits, employee task allocation, and postage delivery routes. Amazon is the world's largest e-commerce website with over 200 million active customers. Optimizing delivery routes is essential not only to make sure that customers get their items on time, but also to save millions of pounds on fuel costs. We have plotted the location of every Amazon fulfillment warehouse onto our map of the United Kingdom, with a set of possible connections between them. The aim is to get as many goods from the source warehouse in Hemel Hempstead to the sink warehouse in Dunfermline. Each warehouse is connected to at least one other warehouse, with the capacity of the edge between them defining the maximum number of trucks that can be moved between the two locations in a single day. As with the last example, we begin by initializing our residual graph with a flow of 0. Starting at the source, we have 3 possible shortest augmenting paths, each of length 4. We may choose any of these, and for the example, we will choose S, B, C, E, T as our first augmenting path. The minimum residual capacity of this path is 25. And so we now update our residual graph, subtracting 25 from each edge in the path and adding 25 to their respective backwards edges. At the next step, we find that the shortest augmenting paths no longer include the edge ET, and has effectively been removed from our calculations. Our shortest possible paths are now all of length 5. We will choose S, B, D, E, F, T, which has a minimum residual capacity of 15. Updating the residual graph with this augmenting path, we subtract 15 from each edge in the path and add 15 to their respective backwards edges. We now have 40 flow going into the terminal, and both ET and EF have been made critical. As a result, we can no longer find any further augmenting paths, as there are no remaining ways to reach T from E, and so the algorithm will terminate with max flow of 40.
We will now explain the time complexity of the algorithm. On each step of the loop, the algorithm finds an augmenting path from the source to the sink. This uses a breadth-first search, which has a time complexity of big O of V plus E, where V is the number of nodes in the graph, and E is the number of edges. As this is a connected graph, we can assume that V must be less than or equal to 2E, as each vertex must have at least one incident edge. This means that big O of V is equal to big O of E, and so the complexity of big O of V plus E can be reduced to big O of E. Thus, each augmenting path in the algorithm can be found in big O of E time. Likewise, updating the residual graph of the augmenting path takes time big O of V, which as shown previously is equal to big O of E, giving a total time of big O of 2E for each iteration of the algorithm. However, as constants are ignored in big O notation, we know this can be reduced to big O of E. Next, we need to find the maximum number of times that the algorithm will iterate. We assume 3 things based on our augmentation rules. Firstly, that the distance between the source and the sink in each augmenting path found will not decrease, as the algorithm finds and uses the shortest path at each step. Secondly, that the maximum number of edges in an augmenting path is V minus 1. And thirdly, that between 2 successive inclusions of the same edge in the augmenting path, the distance from the source to the sink must increase, and it has to happen at least every E plus 1 times. By rules 2 and 3, we see that every E plus 1 iterations, the augmenting path size must increase by at least 1, and that the path size cannot surpass V minus 1, giving a maximum number of iterations of V plus 1 by V minus 1. Therefore, the maximum number of iterations of the loop is given by big O of E times by V. We can now get the complete formula for the time complexity of the algorithm by putting this information together with what we found was the time taken at each step. Therefore, the total running time of the algorithm is given by big O of E times by V times by E, which is equal to big O of E squared by V.